Chapter 9 discusses muscle tissue and how it works, its physiology, whereas most muscles, meaning the organs, are a focus of Chapter 10, if I remember correctly, which we don't explicitly lecture on, because that's anatomy, so that's practicum stuff. So it's already worked in to your practicum 1 and practicum 2 study guides, okay? Therefore, the next chapter will be chapter 11. Anywho, muscle tissue is heavy stuff. It makes up almost half of your mass. Very highly vascularized, in part, or this may help you remember that it's highly vascularized. Muscle cells and neurons are the biggest spenders in your body. They will go through nutrients and oxygen as fast as possible, sometimes faster than the circulatory system can actually deliver, which we'll come back to more in 242. I think of muscle tissue as being a bit snobbish, pish-posh, because there are all sorts of prefixes and roots that mean muscle, and we tend to replace a lot of the general biological terminology with these roots and or prefixes, which personally just makes me want to pull my hair out of my head. So the prefixes that mean muscle include myo, mys, M-Y-S, and sarco. And the hair pulling, an example of the hair pulling would be, rather than saying that a muscle cell has cytoplasm, well, they're pish-posh. So we say that a muscle cell has sarcoplasm. Isn't that horrible? Like you didn't already have a hard enough time with cellular components. Rather than saying that a muscle cell has endoplasmic reticulum, which it absolutely does, we say that it has sarcoplasmic reticulum. I know. The plasma membrane of a muscle cell, oh no, that's not a plasma membrane, even though it totally is. That's a sarcolemma. Isn't that horrid? So as much as possible, I'll continue to translate through the lecture, so that hopefully by the time you're taking an assessment, you can easily translate on your own. Okay. Muscle cells are equipped with the machinery, certainly, to transform chemical energy into mechanical energy. And one of the key components that allows muscle cells to do that are myofilaments, which may or may not be present in other cells, but they're present in such number and in such arrangement or configuration in muscle cells that they work together and can achieve contraction. Those myofilaments can potentially be part of the cytoskeleton of any sort of cell, but again, because of their number and their arrangement in muscle cells, they are called myofilaments. Okay, and their flavors, if you will, are actin and myosin. We'll come back to those so many times in this file and in this chapter. Actin and myosin. Okay. Next slide. All muscle tissue is excitable, or if it's easier for you, you may use the word responsive. In other words, muscle tissue is an effector. And just in case you're rusty, and because it's so important, let's review. What are the four, or who are the four effectors in the human body? Good. Smooth muscle, skeletal muscle, cardiac muscle, and glands with a D. Glands. Good. All muscle tissue is contractible. It's able to shorten. The cells are able to shorten and therefore really shorten an entire organ. And that's called contraction. Okay? They're all able to exert force. All muscle tissue is extensible and elastic. It's able to stretch and recoil back into its original form, which is a set of characteristics that we also saw in, for instance, dense elastic connective tissue. Stretch and recoil. Snap back. All right, let's look at the next slide, which I think is a bit skimpy. We're gonna add some at the bottom of the slide and maybe off the top of my head as well. Muscle tissue functions in movement, but doy or duh. Okay, movement of what? Movement of various fluids into, out of, and through the body. Movement also to allow us to locomote. Movement also to allow us to manipulate, right? So it's really, and express ourselves, really vague to simply say move. There's so much that falls into that category. Muscles allow us to maintain our shape to some degree, our posture, our position, certainly. They help to stabilize our joints. Maybe you recall in Chapter 8, the greater the muscle tone, the more stable the joint. Because muscle cells are big spenders, one of the byproducts of that busy metabolism is heat. Which I think we talked about maybe even in Chapter 1. When you shiver, you generate heat and raise your body temperature, at least temporarily. Muscles help to provide defense barriers. So yet another layer to minimize infiltration or infection. Minimize water loss. Minimize heat loss. If I just had skin and hypodermis, superficial to my rib cage, then my thoracic organs would be far less protected, okay? Our muscle tissues help to form valves to prevent the backflow of fluids. They help to control our, the diameter of our pupils in our eyes, and therefore help us to achieve both distant and near vision. Muscle tissue achieves, of course, erector pilification, the erection, if you will, of our body hairs. right, via erector pili muscles. Let's see, I feel like there was something else I wanted to mention here. Yeah, let's actually throw another one here into movement. It's not just necessarily about propelling fluids. Sometimes it's about mixing fluids. And we'll come back to that. Maybe even this chapter, I don't remember. Is there anything else I wanted to mention? I'm sure there is, but that's all I can think of right now. Anyway, a much healthier list than what was originally on the slide. Let's move to the next slide. There are 3 different types of muscle tissue. You already know that. Skeletal muscle, cardiac muscle, and smooth muscle. And this is our first time officially meeting them, though remotely, through a microscope, okay? And therefore, we'll really go slowly through some of the techniques and signs, landmarks that you would need to know in order to successfully identify each of these, okay? Just like we did with Chapter 4 epithelial tissues and Chapter 4 connective tissues, all right? This is kind of a conundrum that it's not that big of a deal. I'm not going to ding you if you say this incorrectly, but skeletal muscle cells are really, really long. Smooth muscle cells aren't necessarily long, but they're certainly elongated. They're much, much longer than they are wide, okay? Therefore, it's okay to call a skeletal muscle cell a skeletal muscle fiber. Same thing. It's okay to call a smooth muscle cell a smooth muscle fiber. Same thing. All right? But for whatever reason, I mean, really because of their shape, they're not guaranteed to be longer than they are wide. Cardiac muscle cells, we try not to refer to as muscle fibers. So I say just cover your butt and just always use the phrase muscle cell. Cardiac muscle cell, yeah, that's a thing. Smooth muscle cell, yeah, that's a thing. Skeletal muscle cell, yeah, that's a thing. Okay, but be aware that if an author uses the phrase muscle fiber, they're probably referring to skeletal or smooth muscle and not cardiac muscle. All right, let's start with skeletal muscle. Although we'll better develop our understanding of what we're seeing in skeletal muscle later in the chapter, soon, but not right away. In other words, we're going to zoom way in and really better understand why it is we're seeing what we're seeing. Okay. Hopefully you know I'm on slide 6. Skeletal muscle cells are found in the organs called skeletal muscles. And they're called skeletal muscles because they typically attach, at least on one end, to bone, though another attachment possibility is skin. And that's actually how we achieve facial expression, by moving our skin around. No wonder smiling gives you wrinkles. So does frowning. Skeletal muscle is most often referred to as voluntary. Really, every author, it's conventional to refer to it as voluntary. However, that gives me the heebie-jeebies because I think it's so misleading. It suggests that if I put my hand on a hot burner on a stove, that I have to stop and decide which muscles I want to volunteer to contract and which muscles I want to volunteer to not contract, and then finally remove my hand from the burner. If I wait that long, I've got third-degree burns. So personally, I don't use the term voluntary. or it's not my preference personally. I use the term willable. You can will your skeletal muscles, meaning the organs, to contract. You can will your skeletal muscles to relax. That doesn't mean you have to. That doesn't mean you have to be cognizant. That doesn't mean that you have to decide or know which muscle to do what with. Everything's already hardwired. Okay? Nor does it mean that you can't contract a skeletal muscle without willing it to contract. Willable. Your skeletal muscles don't have to be willed in order to contract or relax, but they can be. Hopefully that makes sense for you. Again, skeletal muscle cells are really, really long, so sometimes they're called skeletal muscle fibers. We will actually use the term fiber just once in order to help us with a mnemonic, and that's it. And we'll do it later. The skeletal muscle cells are certainly the longest of all the muscle cells. There's some of the longest cells in your body. I would argue that the longest cells in your body are some of your neurons, because some of your neurons are a meter long, or they can be a meter long. That means that if you're a classic Star Trek alien, approaching or at 7 feet tall, then it's possible to span your length with just 2 neurons. That's crazy. I'm so impressed. Skeletal muscle cells are so big, so long, that the city is just too big. It's too big to have only one post office. It needs more service. Okay, so skeletal muscle cells feature many, each one features many nuclei. Okay. Because of the number of actin and myofilaments, I just said myin. Actin and myosin filaments, and the very, very regular formulaic arrangement of those numerous actin and myosin filaments in skeletal muscle appears to be striped. It's really an optical illusion. It's not as if skeletal muscle is trying to wear a certain style. It's not like it's the most fashionable tissue you've got, okay? But the arrangement, and I'll walk you through that later, I promise. The arrangement of actin and myosin, especially in such great number, creates this illusion that skeletal muscle is striated. Striated. It features striations. I mean striped. All right. Skeletal muscle can contract very, very quickly, but it also tires very, very quickly. It can exert a lot of power, but it also tires very, very quickly, okay? And you will contrast skeletal muscle with at least cardiac muscle in much greater detail in 242. So there'll be even more to learn in 242 about these muscle types. Let's look at the next slide. Same layout that we've seen before in chapter 4, where we were given a micrograph to help us practice. The tissue is described, its function is laid out, its locations are laid out, okay? And a skeletal muscle cell looks like this guy, okay, but longer. Right, this has been cut. All right, which means that at this scale, in order to complete, to show the entire length of a skeletal muscle cell, we'd go off the screen. This represents part of a skeletal muscle cell. There's its neighbor. Right? They'd run right off that screen. There's just not enough room to depict all of them. Here's another. Hopefully you're appreciating how parallel these guys are to each other. Maybe if I was going to finish that one, it would be... Well, actually, I made it too skinny. I still made it too skinny. Maybe I should give up. Wise up, Tessa. Silly. Right? The striations that I mentioned earlier, and I'm going to zoom way in, are these guys. Oh, that's way too thick. Let's go tiny as it gets. Here's a nice wide striation. Okay, here's another wide striation. Here's another wide striation. Okay, but notice that in between them is a super skinny pinstripe of a striation. You guys see that? So not only is this striated, but it's got alternating wide, skinny, wide, skinny, wide, skinny, wide, skinny striations along its entire length. And again, I'll talk to you about why later. This guy, who's got a radius? This guy. That's a nucleus. Okay. That's a nucleus. That's a nucleus that belongs to the same cell. That's probably a peekaboo of a nucleus that belongs to that same cell. Here's a nucleus that belongs to that same cell. At this scale, the cell already has 5 nuclei. Good grief. Multinucleated. Okay. Willable. Right? And examples of skeletal muscles. Maybe you know deltoid. Maybe you know pectoralis major. Maybe you know biceps brachii. Maybe you know gastrocnemius. I don't know why, but I was really little when I learned gastrocnemius. Weird parents. Maybe you know biceps femoris. Oops, where? Latissimus dorsi, maybe? for the trapezius muscles. Okay, but hopefully you also know plenty of skeletal muscles associated with the axial skeleton, because I would think that by this time in the quarter, you've already started studying axial muscles. Therefore, we could put zygomaticus major or minor in here. We could put levator, labii superioris in here. We could put the buccal in here. Corrugator supercilii, epicranius, so on and so forth. Sternocleidomastoid. Anyway, chances are you, even before enrolling in this class, knew many examples of skeletal muscles, meaning the organs. You just maybe didn't refer to them as skeletal muscles. Okay, let's move on to cardiac muscle. But again, I will come back to the nitty-gritty of skeletal muscle again, because it's a huge focus of this chapter. Cardiac muscle makes up most of your heart. Why doesn't it make up all of your heart? Well, your heart is an organ, and by definition, an organ is comprised of at least 2 tissues. So is your heart made entirely of cardiac muscle? No, it can't possibly be. For instance, it is lined with what? Crossing my fingers. Good. Simple squamous epithelium. Good. You'll learn lots about the heart, like intense, in 242. Okay? Cardiac muscle is said to be involuntary. What does that mean? You can't will it to contract or relax even on the bad days. The heart features both contractile cardiac muscle cells, like classic muscle cells, and pacemaker or autorhythmic, very highly modified cardiac muscle cells that look like cardiac muscle cells, contractile type, but function a lot more like a neuron. They can generate nerve impulses on their own without the nervous system. Isn't that cool? That means you could be brain dead, but your heart can still beat. Wow. But the nervous system can make adjustments in the force and rate of your heart's efforts, and therefore can change what your heart is doing to better reflect what's going on in the environment. Your pacemaker cells don't get any information about the environment. So if you're being chased by a bear, or worse, a zombie bear, and you're just relying on your pacemaker cells, the special autorhythmic cells in your heart, you're not going to escape that bear. Your heart rate isn't going to increase enough to complement the use of your skeletal muscles. Your skeletal muscles are going to start to use up oxygen and nutrients really, really quickly because you're trying to run away, but your heart's not going to keep pace with that. Anyway, that's what all this hubbub is about. Zombie bears. Cardiac muscle cells are not typically referred to as muscle fibers. I'm sorry. I know, it's evil. But the arrangement and number of actin and myosin filaments does allow that sort of optical illusion of striation. Each cardiac muscle cell will typically feature one nucleus, only one nucleus, rarely two. Rarely two. And the two distinguishing characters of cardiac muscle tissue are, branching cells. So let's say that we have this shape-ish of a muscle cell, whereas a cardiac muscle cell I'm really emphasizing the idea of branching, might look like this. Branching, okay? And between adjacent cells, so here's maybe an adjacent cell. Here's maybe an adjacent cell. Here's an adjacent cell, okay? Are these reinforcing sort of reinforcements that are called intercalated discs. And an intercalated disc features oodles of desmosomes, bolt-like connectors, because you cannot regenerate cardiac muscle. You can't, if a cardiac muscle cell dies, you can't replace it with another cardiac muscle cell. So your heart has to last your entire lifetime. And yet, it's spending all day, every day of your lifetime trying to rip itself apart. It exerts so much force that without these extra desmosomes, the heart would rip itself apart. Isn't that crazy? I love it. And intercalated discs also feature oodles of gap junctions. Oops. Oh no, not an oops. That looked funky for a hot second. Gap junctions allow the nerve impulses. We'll replace that term later, by the way. That command the contractile cardiac muscle cells of the heart to contract, to be relayed from one cardiac muscle cell to the next very rapidly, even faster than, say, neuron to neuron, because there's no space across which, for instance, neurotransmitter has to flow, because these cells are immediately connected with each other, and they even share these portals, these gap junctions, lots and lots. So it allows the heart to really function as one unit. All those cells are functioning as one unit. And we'll come back to that in 242. Let's go to the next slide, which is 9. All right. Here's a lovely micrograph. There's a branch. Well, there's a teeny branch here. And a teeny branch here. This may be a branch. The branching event, if you will. Okay. Whereas this guy, that's an intercalated disc. Here's another Another. Another. They don't have to be huge. Okay. And if you zoom way in, oh yeah, I do see like a really subtle striation pattern, right? Is that striation easy to see throughout the entire micrograph? No, it's a little harder to see here, right? And it's a little easier to see through these thinner areas. I can really see it down here. Anywho, not willable, only found in the heart, but not the only thing that the heart is made out of. Let's talk about smooth muscle. Smooth muscle is found in the walls of all of your hollow organs, all of your hollow viscera, except for your heart, of course. Okay, that's a lot of places. So if I ask you to list 8, maybe even 10 locations of smooth muscle, that's actually reasonable. That's not that bad. You have smooth muscle in many, but not all, of your blood vessels. You have smooth muscle in your ureters and your urinary bladder. You have a smooth muscle as well as a skeletal muscle, urethral sphincter. You have a smooth muscle as well as a skeletal muscle, anal sphincter. You have smooth muscle in your uterus, if you have a uterus. You have smooth muscle in your esophagus, in your stomach, in your small intestine, in your large intestine. You have lots and lots of options if I ask you where to find smooth muscle. Okay? Your erector pili are also smooth muscle. Hopefully you recall that. And then this is going to come back to us this quarter anyway, so it's certainly okay to preview it. Our eyes, our eyeballs, how about that, have muscles inside that help to regulate the shape of our lenses. We also have muscles inside our eyeballs that help to regulate the diameter of our pupils. Okay? But you also have, that's another thing we could list under skeletal muscle, or functions. Anyway, you also have muscles on the outside of your eyeballs that steer your eyeballs up, down, to the side, medially. Okay, and for that matter, you have nearby skeletal muscles that operate your eyelids. Okay, so when we're talking about the muscles that are inside your eyeballs, those muscles are smooth muscle. Okay, whereas when we're talking about those that are outside your eyeball, those are skeletal muscle. Those that are inside are called intrinsic, and those that are on the outside are called extrinsic. Doesn't mean they're outside your body, they're just outside the eyeball. Okay, so that's what this little note here, whoops, there we go, is referring to. Okay, you have smooth muscle in at least most of your lower respiratory tree. So like most of the tunnels headed to and through your lungs will feature smooth muscle as well. And that's something you'll come back to in 242. Smooth muscle is not willable. Not willable. Some smooth muscle is able to contract depending on where it is, without stimulation from the nervous system, like cardiac muscle, but some is not. The smooth muscle associated with your digestive system does have sort of an autorhythmic aspect, but you'll come back to that in 242. I wouldn't focus on that too much in 241. Smooth muscle cells are sometimes called muscle fibers, unfortunately. They are not striated, which lots and lots of students misunderstand. Actin and myosin are present. Where did my... Maybe. There we go. Frankly, this wouldn't be a muscle tissue if actin and myosin weren't there. Okay? They're just not as numerous or as regularly arranged. Therefore, they don't create the illusion of stripes. Okay? Each smooth muscle cell has only one nucleus, and smooth muscle cells, not only are they long, but they taper at their ends. They're spindle-shaped, okay? Which also typically forces the nucleus to be spindle-shaped and centered. Really cling to that, and that will help. Next slide, which is 11. In this micrograph, some of those sort of taperings are more evident than others. Oh, let's switch colors. So that is at least part of a smooth muscle cell. Okay, and certainly that same nucleus also has a tapered quality to it. This one's got a nice tapered quality to it, okay? Now, I'm going to pause this program, Notability, so that I can take you, during the video, record, to another file that you actually don't have, because I want you to practice. And the reason why you're going to need practice is because very often smooth muscle tissue looks like dense, regular connective tissue. They're the two most commonly mixed up. Oops, that's the wrong letter. Tissues. So they take some practice. I'm going to show you some. Oh, sorry, you guys. I'm going to show you some clues. Okay, hold on. Gotta switch files. Oh, good. It's already there. Oh, where did I put it, though? Good. All right. Actually, I want to skip that one. Let's do this one. All right. One of these micrographs is a photo of dense, regular connective tissue. And one is a photo of smooth muscle tissue. Notice that this one has, oh, I don't think I can write on here. Well, I guess I'll just make motions. Has a slightly wavy attribute to it. Just a little ripple Can you kind of make that out? Just a little ripple. Okay. Also notice that rather than being within what looks like a fiber, the nuclei end up alongside fibers, and they end up, oh, oops, I can use the pen, just not for the right thing. They end up aligned. Okay. This micrograph is taken at a greater magnification, so that's a little bit tricky. Look how much larger this nucleus is than that nucleus. That's a hint that they're not at the same magnification, right? I'm not seeing the wiggle, but it's possible that I'm just too zoomed in, all right? But notice that this nucleus, it looks as if it's sitting within a fiber. This one looks like it's sitting within a fiber, within a fiber, within a fiber. That's because these aren't fibers. These are smooth muscle cells, okay? Whereas this is dense, regular connective tissue. Isn't that tough? So personally, I use all the landmarks I can find. All right. One of these is dense, regular connective tissue, and the other one is smooth muscle tissue. Which is which? And these are roughly at the same magnification. Does one of them have a little bit of a wiggle? Does one of them depict nuclei in the center of fibers? Can you discern any tapering? Any tapering? In other words, do most of the nuclei look like this shape? Tapered on the ends? Or do any of the cells look like this shape? Tapered on the ends? And do you see multiple nuclei aligned? Not just one line of nuclei, but more than one. Right? This is much more difficult. This one is dense, regular connective tissue. And this one is smooth muscle tissue. Look for all of the landmarks. The ripple, this one does have a bit of a ripple, thank goodness. Aligned nuclei, aligned nuclei, aligned nuclei, and very tapered cells with very tapered nuclei within. And hopefully that will help. It can be really tough. Anywho, again, smooth muscle is unwillable and makes up a good portion of the walls of your hollow organs. Moving on to slide 12, we're now going to zoom in even more, really. Recall that skeletal muscle is a type of tissue, but it's also the name that we use for the organs that are comprised primarily, but not entirely, of skeletal muscle tissue. Pardon me. And those skeletal muscles, meaning the organs, they have 3 guaranteed features, but boy, are we going to go into more detail than this. They're innervated pretty richly. They're vascularized also very richly. And one reason why we want them to have lots and lots of nerves is because we need to know, we need that feedback as to, where we are in space. We also need to know when there's an issue. We need to be able to feel pain. One of the reasons why we want that fairly rich vascularity is because, again, muscle cells are big spenders. They perform cellular respiration as long as oxygen is available, like cray-cray. All skeletal muscles, meaning the organs, have connective tissue sheaths. Connective tissue sheaths. And a sheath is like a sleeve. You know how your sleeves go over your arms? Well, these connective tissue sheaths, they're like sleeves that go over different units within the skeletal muscle, main organ, but also around the entire organ. Okay, it's kind of like an encasement. Okay, and these sheaths help to compartmentalize the different units, the different aspects of the organ. Okay. And I'll go over this again, don't worry. But because of those connective tissue sheaths, a single skeletal muscle, for instance biceps brachii, is made up of many fascicles. The organ has a connective tissue sheath around it, but each fascicle has a connective tissue sheath around it. So it's very easy to see that there are units within the entire organ. And yay! Each fascicle is comprised of many, many fibers. And here, what we mean by fibers is cells. Muscle fibers, muscle cells, same thing. Okay? Each of these has a connective tissue sheath around it. Okay, so if we're zoomed in enough, we're using our microscope, okay, a really powerful microscope, but a microscope, then wow, you can even see pretty distinct individual cells because they each have a connective tissue sheath around them. Okay. Each skeletal muscle cell or fiber is in turn a big old bundle of myofibrils. Myofibrils, and I'll show those to you. And each myofibril is a big old bundle of myofilaments. And the myofilaments we've actually already met. These are actin and myosin. So here's how I kind of picture this. I've got a whole bunch of angel hair pasta. And I put a rubber band around it. But you know what? I really like angel hair pasta. So I've got enough to make 2 servings. I've got enough to make 3 servings. And that's right about the time when I get too lazy. All right. I'm going to take these 3 servings and call them a meal. Okay. And I'm going to bundle those together. Okay. And we're going to call that Monday night dinner. But you know what? What about Tuesday night? There are 3 people in my family on Tuesday night, too. Oops, wrong color. I think. The same color? Yeah. Okay. And even though I really want to stop drawing, If you're getting tired of me drawing, imagine how it feels to actually be doing it. You're not allowed to complain. Only I get to fuss. Wednesday night. And then I guess the rest of the week we order pizza. I don't know. Anyway. Then I'm going to bundle those together. Okay? And maybe I want to get ready for the whole month. So I'm going to make even more of these big red bundles. Also, I'm going to make a mess out of the slide. I forgot to tell you that. Warning. Okay? And then I'm going to bundle those together. It's like I'm a never-ending supply of rubber bands, huh? Okay? That's very similar, although not, to what we see in skeletal muscles, okay? Where that green might be the connective tissue sheath around the entire muscle. And this red might be the connective tissue sheath around a fascicle, for instance. In other words, a skeletal muscle, meaning the organ, is a bundle of bundled bundles. Now, just in case my doodle isn't doing it for you, thank goodness we've got a professional illustrator. Next slide, please. All right, here's the entire organ, right? And sure enough, it's encased, it's enrobed, it's sleeved in a connective tissue sheath. Okay? And see these guys? Each of those is a fascicle. A fascicle. And the illustrator has even chosen a fascicle and pulled it out of the screen toward us so that we can see, sure enough, oh yeah, there's a connective tissue sheath around that. Okay. Pardon me. I wonder what that makes these. What are these things? Each skeletal muscle is a bundle of fascicles. Each fascicle is a bundle of, yeah, these are muscle cells, muscle fibers. Okay. And again, the illustrator chose one and pulled it forward out of the screen for us. And not so evident in this top big illustration, but much more evident here. I inserted this one into this particular slide. Oh yeah, there's a connective tissue sheath wrapped around an entire cell. Oh yeah. Okay. What does that make these guys? You can probably barely tell that I'm drawing on the slide right now because they're so tiny. They're so tiny. What are those guys? Yeah, those are myofibrils. Okay. And at this scale, I can't see myofilaments. I can't see them. Okay. Now, I want to show you a trick. I have to find a space to do it. I think I'll do it right here. But just use really tiny font. I never have to study my different subunits of skeletal muscles because I have a mnemonic. So if the question is what are the subunits of a skeletal muscle, meaning the organ, then every time, without studying, without having to look it up again, I can list my subunits in order from largest to smallest, okay, without fail. Let me show you my trick, what I'm doing. I'm alphabetizing. FA comes before FI, F comes before M, of course, MYOFIB comes before MYOFIL. Okay? Notice that this mnemonic forces you to use the word fiber rather than cell. You'd mix it up if you use cell. Okay? And then personally, I draw my list in this kind of stepwise fashion. Just to remind me, myofilaments are nested within myofibrils. Myofibrils are nested within fibers. Fibers are nested within fascicles. Fascicles are nested within the organ. So hopefully that helps. If not, hopefully you find some way that works for you. Just because I have a tool doesn't necessarily guarantee that it works for your brain. But I try. All right, let's move. Oh, I forgot to tell you. On the previous slide, the one that I made a mess of, so it's no wonder that I forgot to tell you, another character or feature that skeletal muscles all have, they all have attachments, okay? And that's actually the nitty-gritty of the next slide, which is 14. We already expect skeletal muscles to attach to bone or I guess I should say and or. Oh, I'm still in that teeny tiny font from the previous scribble. Skin, which always makes me think facial muscles. Not that they're the only skeletal muscle that attach to skin, but it's an easy one to remember. We already know that every skeletal muscle attaches to bones and or skin in at least two places or at least 2 points. An insertion, although some have more than one insertion, and an origin, although some have more than one origin. Okay, origin is the anchor. Remember, you were sitting down with the rope. And the insertion is where the action actually takes place. It's the part that gets moved. All right? Connective tissue sheaths typically extend beyond the, say, end of a skeletal muscle and attach, blend into perichondrium, say, for a joint, periosteum of the corresponding bones, okay, and or fascia. And a fascia is a very sleeve-like, very sheet-like anchor. Kind of like, let's take a tendon and flatten it out as much as we possibly can, okay? Aponeuroses. I'm not sure where I left off, so I'm sorry if this is a repeat. When those connective tissue sheaths extend beyond the muscle, like behind the end of a muscle, okay, they form tendons, which are rope-like, or aponeuroses, which are sheet-like. And I think I just established that fascia are sheet-like. So you're probably asking, what's the difference? Almost nothing. Okay. An aponeurosis can also be called an necrotic fascia. Okay, another way to say that, although I still can't guarantee that I'm not going to confuse you. Aponeuroses, all aponeuroses are fascia. Not all fascia are aponeuroses, okay? And aponeurosis specifically connects skeletal muscle to something, okay? Connects to perichondrium, connects to periosteum, or connects to another sheet. Okay, fascia means sheet. Aponeurosis means sheet that attaches, helps to tether skeletal muscle. All right. In the context of this chapter, they're interchangeable. Totes my goats. All right.